world of digital electronics, where logic meets innovation to power modern technology. This presentation, including all content, visuals, and materials, is the exclusive property of Karnaugh Semiconductor Private Limited. All rights are reserved. Unauthorized copying, reproduction, distribution, or disclosure of any part of this material, in any form or by any means, is strictly prohibited without prior written permission from Karnaugh Semiconductor Private Limited. The company name, logo, and all related marks are trademarks or registered trademarks of Karnaugh Semiconductor Private Limited. This document and its contents are confidential and intended solely for authorized individuals. Any unauthorized use, review, or sharing of this information may result in legal action. Copyright Karnaugh Semiconductor Private Limited. All rights reserved. Let's begin by diving into the fascinating world of Boolean algebra. What exactly is Boolean algebra, you ask? Well, it's a remarkable mathematical system utilized to analyze, and design digital logic circuits. How does it work? It works with binary variables. That's right. Each variable can take only two possible values. Fascinating, isn't it? Those two values are 0, which represents false, and 1, which represents true. Now, in Boolean algebra, we use variables to represent these values. For example, if we use a variable a, when a equals 1, it means the condition is true. When a equals 0, we represent it as a bar, written as a prime or a complement. So remember, a equals 1, a bar equals 0. This concept of a variable and its complement is fundamental in Boolean logic. Next, let's look at the basic Boolean operations. The first operation is AND. The AND operation is represented by a dot, or sometimes simply by writing variables together. For example, A dot B means A and B. The second operation is OR. The OR operation is represented by a plus symbol. So A plus B means A or B. The third operation is NOT. The NOT operation is used to invert a value. It is represented by a bar over the variable, or sometimes by a prime symbol. So NOT A is written as A bar. These three operations, AND, OR, and NOT, form the foundation of Boolean algebra and are used to build all digital logic circuits. Now let's understand the basic Boolean laws, which are essential for simplifying and optimizing logic expressions. We'll go through them one by one. First, identity laws. The identity laws demonstrate how a variable behaves when combined with fixed values. When we perform an OR operation, a plus 0 equals a. Adding 0 does not change the value. When we perform an AND operation, a dot 1 equals a. Multiplying by 1 also keeps the value unchanged. So, 0 is the identity for OR, and 1 is the identity for AND. Second, null laws. The null laws demonstrate how a variable behaves when combined with dominant values. For OR operation, a plus 1 equals 1. If any input is 1, the OR output becomes 1. For AND operation, a dot 0 equals 0. If any input is 0, the AND output becomes 0. Here, 1 is dominant for OR, and 0 is dominant for AND. Third, idempotent laws. The idempotent laws inform us what occurs when a variable is combined with itself. For OR, a plus a equals a. For AND, a dot a equals a. Thus, repeating the same variable does not change the result. Fourth, complement laws. The complement laws describe how a variable interacts with its complement. For OR, a plus a bar equals 1. A variable ORed with its complement always gives 1. For AND, A dot A bar equals 0. A variable ANDed with its complement always gives 0. These complement laws are extremely important for logic simplification. Now let's delve into the commutative law in Boolean algebra. The commutative law informs us that the order of variables indeed does not matter in specific operations. For the OR operation, A plus B equals B plus A. This signifies that the result remains unchanged even if we swap the inputs. Similarly, for the AND operation, A dot B is equivalent to B dot A. Once again, altering the order of the variables does not influence the output. So, whether we express it as A or B or A, and whether we say A and B or B and A, the result stays the same. The logic result is exactly the same. This property allows flexibility in writing and rearranging Boolean expressions, which is very useful during logic simplification and optimization. Now, let's understand the associative law in Boolean algebra. The associative law tells us that the way variables are grouped does not affect the result, as long as the operation remains the same. For the OR operation, A plus B plus C is equal to A plus B plus C. This means we can change the grouping of variables without changing the output. Similarly, for the AND operation, A dot B dot C is equal to A dot B dot C. Again, the grouping can be rearranged, and the result stays the same. So in associative law, the brackets can move, but the operator must remain unchanged. This law is incredibly useful when simplifying complex Boolean expressions, because it allows us to regroup terms easily during logic optimization. Now let's delve into the distributive law in Boolean algebra. This law is without a doubt one of the most powerful tools utilized for logic simplification and optimization. The distributive law elucidates how a single variable can be distributed across a group of variables. Remarkable, isn't it? For the first form, A dot B plus C is equal to A dot B plus A dot C. This means A is distributed to both B and C, just like multiplication in algebra. The distributive law also works in reverse, which is very important. In the second form, A plus B dot C is equal to A plus B times A plus C. Here, the OR operation is distributed over the AND operation. These two forms allow us to expand expressions, factor expressions, reduce the number of logic gates. Understanding the distributive law helps us choose the most efficient logic implementation when designing digital circuits. Now let's learn one of the most important concepts in Boolean algebra, De Morgan's theorems. De Morgan's theorems are used to simplify logic expressions and to convert between and/or forms. This is extremely useful in digital circuit design. The first theorem states the complement of A and B is equal to A bar or B bar. In other words, A dot B prime equals A prime plus B prime. The second theorem states the complement of A or B is equal to A bar and B bar. That is, A plus B prime equals A prime dot B prime. A simple way to remember De Morgan's theorems is invert the variables, change and to or, change or to and. De Morgan's theorems, oh, how widely they are used. To convert logic to NAND or NOR implementations, to simplify complex Boolean expressions, to optimize digital circuits for speed and area. Mastering De Morgan's theorems is indeed essential for efficient logic design. Now let's delve into the fascinating realm of logic optimization, an exceptionally significant concept in the domain of digital design. Logic optimization, you see, is the intricate process of minimizing the number of logic gates, literals, or logic levels within a Boolean expression, all without altering its functionality. In simpler terms, we aim to make the logic smaller, faster, and, oh yes, much more efficient, while ensuring that the output remains absolutely unchanged. Why logic optimization matters? There are several important reasons why optimization is absolutely necessary. First, it reduces circuit area. Fewer gates means smaller hardware and lower cost. Second, it reduces power consumption. Optimized circuits switch less and consume less energy. Third, it improves speed. Fewer logic levels mean less delay in signal propagation. And finally, it simplifies hardware. Simpler designs are easier to test, debug, and maintain. Logic optimization techniques. There are several common techniques used for logic optimization. The first method is algebraic simplification. Here, we use Boolean laws to simplify expressions mathematically. The second method is Karnaugh Maps, or K-maps. K-maps provide a visual way to simplify logic by grouping adjacent ones or zeros. The third method is Boolean factoring. This technique reduces gate count by factoring common terms from expressions. The fourth method involves canonical forms, such as sum of products and product of sums, both of which provide standard representations. These are used in logic synthesis tools. We will discuss each technique in the next slides. Get ready. Summary. Logic optimization. Oh, how it assists us in designing digital circuits that are smaller, faster, more power efficient, and believe it or not, easier to implement. This is precisely why logic optimization serves as a core skill for digital and VLSI engineers. Absolutely. Let's dive into the concept of algebraic simplification, shall we? With a straightforward example, we can grasp its principles. Algebraic simplification, what is it? It's a technique, one of logic optimization, that's utilized to streamline a Boolean expression. By employing the laws of Boolean algebra, we can achieve this reduction, all without altering the circuit's functionality. Isn't that fascinating? Problem 1. Let us simplify the expression, AB plus AB bar. Step 1. Factor A. Both terms contain A, so we factor it out. AB plus AB bar becomes A times B plus B bar. Step 2. Apply the complement law. From Boolean algebra, we know that B plus B bar equals 1. Therefore, the expression transforms into A times 1. Step 3. Apply the identity law. Anything ANDed with 1 remains unchanged. Thus, A.1 equals A. Final answer. So the simplified result is simply A. This means the original expression AB plus AB bar can be implemented using just a single signal A, eliminating unnecessary gates and reducing hardware. This is the power of algebraic simplification in logic optimization. Now let's simplify the Boolean expression, A plus A bar B plus AB. Step 1. Group the terms. First, we group the terms that have a common variable A, so we rewrite the expression as A plus AB plus A bar B. This grouping helps us apply Boolean laws more easily. Step 2. Apply the absorption law. Next, we simplify the grouped expression, A plus AB. According to the absorption law, A plus AB equals A, so the expression now becomes A plus A bar B. Step 3. Final reduction. Now we simplify A plus A bar B. Using Boolean algebra, this expression reduces to A plus B. Final answer. So the final simplified result is A plus B. Conclusion. This simplification removes redundant logic, reduces gate count, and produces a much more efficient circuit. This example clearly demonstrates how algebraic simplification helps optimize digital logic designs. Let's simplify the three-variable Boolean expression, f equals x bar y bar z plus xyz plus x bar yz plus xy bar z. Step 1. Identify the common variable. First, observe that every term contains the variable z. So, we factor z out of the expression. This gives us f equals z times x bar y bar plus xy plus x bar y plus xy bar. Step 2. Group terms inside the bracket. Now, let's simplify the expression inside the parentheses. We group the terms based on x bar and x. X bar times y bar plus x times y bar plus y. Step 3. Apply the complement law. From Boolean algebra, we know that y bar plus y equals 1. So the expression becomes x bar times 1 plus x times 1, which simplifies to x bar plus x. Step 4. Apply the complement law again. We know that x bar plus x equals 1. So the entire expression inside the brackets becomes 1. Step 5. Final simplification. Substituting back, we get f equals z times 1, which simplifies to f equals z. Final answer. So the final simplified result is f equals z. This means the output depends only on z, and the variables x and y have no effect on the final output. This is a powerful example of logic optimization, where a complex three-variable expression reduces to a single variable. Let us now, without further ado, understand what exactly a truth table is. A truth table is in fact a tabular representation that quite clearly shows all possible input combinations of a logic function and the corresponding output. In digital systems, yes indeed, inputs can take only two values, 0 or 1. So a truth table helps us clearly see how the output behaves for every possible input case. Why do we use truth tables? Truth tables are used to understand logic behavior, verify Boolean expressions, design logic circuits, cross-check K-maps and algebraic simplification, debug wrong logic designs. In short, a truth table guarantees that our logic is functionally correct. Two-variable truth table example. Now take a look at the example shown on the right. We have two inputs, A and B, and one output, Y. Since there are two variables, the number of possible input combinations is 2 squared equals 4 combinations. Let's proceed. Row by row. When A equals 0 and B equals 0, the output Y equals 1. When A equals 0 and B equals 1, the output Y equals 0. When A equals 1 and B equals 0, the output Y equals 0. When A equals 1 and B equals 1, the output Y equals 1. Now, let's observe the output pattern. From the table, take note that the output Y is true only for two input combinations, 0, 0, 1, 1. This indicates that the output is high when both inputs are equal. Writing the Boolean expression. Now, we convert the truth table into a Boolean expression. For A equals 0, B equals 0, the minterm is A prime, B prime. For A equals 1, B equals 1, the minterm is AB. So the Boolean expression becomes Y equals A prime, B prime plus AB prime. Final takeaway. So from this truth table, we clearly understand the logic behavior. We derive the Boolean expression, and we confirm that the logic works exactly as expected. This is why truth tables are the foundation of digital logic design. Now, let us indeed understand this three-variable truth table. Here, we have three inputs, A, B, and C, and one output, Y. Since there are 3 input variables, the total number of possible input combinations is 2 to the power cubed, which equals 8 combinations. That is why this truth table contains 8 rows. Observing the output pattern. Let us now observe when the output y becomes 1. When a equals 0, b equals 0, c equals 0, output y equals 1. When a equals 0, b equals 1, c equals 0, output y equals 1. When a equals 1, b equals 0, c equals 0, output y equals 1. When a equals 1, b equals 1, c equals 0, output y equals 1. Notice an important pattern. Whenever c is equal to 0, the output y is equal to 1. Whenever c is equal to 1, the output y becomes 0. Writing the Boolean expression. From the truth table, we write the Boolean expression by identifying the rows where y equals 1. Those rows correspond to the minterms a, b, c prime, a, b, c prime, a, b, c prime. So the Boolean expression becomes y equals a prime b c prime plus a prime b c prime plus a b c prime. Key insight. Even though the function is defined using 3 variables, the output depends only on the variable c. This entire expression can later be simplified to y equals c prime. Conclusion. This example clearly demonstrates how a truth table lists all input combinations, helps us derive the Boolean expression, reveals opportunities for logic simplification. That's why truth tables are a foundation of digital logic design. Let us now introduce Karnaugh maps, commonly called K-maps. What is a Karnaugh map? A Karnaugh map is a graphical technique used to simplify Boolean expressions. In simple words, a K-map helps convert a complex Boolean expression into a minimum gate implementation. Instead of repeatedly applying Boolean algebra rules, K-maps allow us to visually identify and eliminate redundant logic terms. Why are K-maps needed? Let us understand the motivation. First, consider algebraic simplification. Algebraic methods depend heavily on human intuition. They may not always lead to the minimum logic form. They can become difficult as the number of variables increases. Now, compare this with K-maps. K-maps provide a systematic and visual method of simplification. They guarantee a minimum SOP or POS expression, which directly translates to fewer logic gates, lower propagation delay, and reduced power consumption. Key takeaway. So, whenever we want, guaranteed minimum logic, reduced hardware, faster and more reliable designs, Karnaugh maps are the preferred tool. Now let us understand the basics of a 2-variable Karnaugh map, or 2-variable K-map. Input variables and combinations. In this case, we have 2 input variables, named a and b. Since each variable can take only 2 values, 0 or 1, the total number of possible input combinations is 2 raised to the power 2, which equals 4 combinations. K-map size. Because there are 4 input combinations, the 2-variable K-map is arranged as a 2x2 grid. Each cell in this grid represents one minterm from the truth table. So every possible input combination of A and B has exactly one corresponding cell in the K-map. Gray code arrangement. Important rule. Now, an important rule to remember. K-maps use gray code order. Gray code ensures that adjacent cells differ by only one variable. For example, the correct gray code sequence is 0, 0, 1, 1, 10. This arrangement is absolutely crucial. It allows us to group adjacent cells correctly during simplification. 2-variable K-map layout. Now take a look at the K-map layout shown below. Rows represent variable A. Columns represent variable B. The top row corresponds to A equals 0, while the bottom row corresponds to A equals 1. Similarly, the left column corresponds to B equals 0, and the right column corresponds to B equals 1. Key takeaway. So, to summarize, a two-variable K-map has two inputs. 4 total combinations. A 2x2 grid uses gray code order, and each cell represents one minterm. This forms the foundation for grouping and simplifying Boolean expressions. Let us see how to fill a two-variable Karnaugh map using the truth table. To fill the K-map, we always start with the truth table. For every row in the truth table, if the output is 1, we place a 1 in the corresponding K-map cell. If the output is 0, we place a 0 in the corresponding K-map cell. So each truth table row directly maps to one K-map cell. Meaning of each cell. Each cell in the K-map corresponds to a minterm when we are working with sum of products, SOP, or a maxterm when we are working with product of sums, POS. This means the K-map can be used for both SOP and POS simplification. Understanding the layout. Look at the K-map shown below. The rows represent variable A. The columns represent variable B. For example, row A equals 0 and column B equals 0 corresponds to input AB equals 0, 0. Row A equals 0 and column B equals 1 corresponds to 0, 1. Row A equals 1 and column B equals 0 corresponds to 10. Row A equals 1 and column B equals 1 corresponds to 11. Key takeaway. So remember, use the truth table to fill the K-map. Place 1s for output 1 and 0s for output 0. Each cell represents exactly one input combination. Once the K-map is filled, we are ready to group adjacent cells and simplify the logic. Now, let us delve into the most crucial aspect of Karnaugh Maps, the grouping rules. Correct grouping is, without a doubt, the key to achieving a minimal Boolean expression. Basic grouping rules. First rule, groups must contain powers of 2 only. This means valid group sizes are 1 cell, 2 cells, 4 cells. Any other grouping size is not allowed. Second rule, groups must be rectangular in shape. This means groups can be horizontal or vertical. L-shaped or irregular groups are not allowed. Third rule, groups can wrap around the edges of the K-map. In other words, the leftmost column is adjacent to the rightmost column. The top row is adjacent to the bottom row. This wraparound property allows additional grouping opportunities. Fourth rule, diagonal grouping is not allowed. Cells that touch only at the corners cannot be grouped together. Final and most important rule, always form the largest possible group. Larger groups eliminate more variables, which directly results in simpler logic. Understanding the diagram. Now look at the K-map shown on the right. The green box represents a valid group of 4 cells. The red and blue boxes show smaller valid groups. The example highlights how grouping size affects simplification, valid group sizes, and variable elimination. Let us indeed examine the table presented below. A group of 1 cell eliminates 0 variables. A group of 2 cells eliminates 1 variable. A group of 4 cells eliminates 2 variables. A group of 8 cells eliminates 3 variables. So remember, a bigger group means fewer variables and fewer gates. Key takeaway. To summarize, use only power of 2 groups. Form rectangular groups. Use wraparound edges. Avoid diagonal grouping. Always choose the largest possible group. These rules ensure that your K-map simplification is correct and minimal. Now, let us understand an important concept in Karnaugh Maps called the wraparound rule, and then see how we derive the Boolean expression from each group. Wraparound rule, edge adjacency. In a Karnaugh map, edges are adjacent, not separated. This means the left edge is adjacent to the right edge. The top edge is adjacent to the bottom edge. So even though the cells appear far apart on the diagram, they are considered neighbors in K-map logic. This property allows us to form larger groups, which leads to simpler Boolean expressions. Understanding the example. Now, look at the K-map shown below. You can see two adjacent ones placed in the top row, even though they are at the left and right edges. Because of the wraparound rule, these two cells are adjacent and can be grouped together, deriving the Boolean expression from the group. Now, let us derive the Boolean expression from this group. In this group, variable b changes from 0 to 1. Variable a remains constant at 0. So we eliminate b and keep a bar. The simplified expression becomes y equals a prime. Why K-maps are powerful. If we solve this using algebra, it would require multiple steps. But by using a K-map, we visually identify adjacency, eliminate changing variables, and directly write the simplified result. So instead of a long expression, we simply write y equals a bar. Now, let us understand the two types of Karnaugh maps, and also look at some common mistakes students make while using K-maps. SOP versus POS, two types of K-maps. Karnaugh maps can be utilized in two distinct forms. The first one is SOP, which stands for sum of products. In SOP, we group the ones in the K-map. Each group produces a product term. All product terms are then ORed together. The second type is POS, which stands for product of sums. In POS, we group the zeros instead of the ones. Each group produces a sum term. All sum terms are then ANDed together. In practice, most digital circuit designs utilize SOP because it is simpler and more commonly implemented. Common student mistakes. Now let us look at some frequent mistakes to avoid. First mistake, ignoring gray code order. If gray code is not followed, adjacency rules will break and grouping becomes invalid. Second mistake, grouping diagonally. Diagonal cells are not adjacent and cannot be grouped. Third mistake, using non-power of two groups. Valid groups must be 1, 2, 4, 8, and so on. Fourth mistake, making smaller groups when a larger group is possible. Smaller groups lead to more variables and more gates, which is not optimal. Summary. Let us summarize what we learned about two-variable K-maps. A two-variable K-map has 4 cells. It uses gray code arrangement. We group adjacent ones for SOP. We eliminate changing variables. And finally, we obtain a minimum logic expression. Final takeaway. If grouping rules are followed correctly, then Karnaugh maps provide a fast, visual, and guaranteed minimum solution for Boolean simplification. Let us indeed work through a two-variable example using Karnaugh maps. The function is given as f of a and b equals the summation of minterms 1, 2, and 3. This notation means that the output f is equal to 1 for minterms m1, m2, and m3. Step 1. Prepare the truth table. Our first step is to prepare the truth table based on the function definition. Since we have two variables a and b, there are 4 possible minterms from n0 to n3. Assigning output values. Now, we assign values to the output column f. For m1, n2, and m3, the function is true, so we assign 1. For m0, the function is not listed, so we assign 0. This gives us the truth table shown below. Understanding the table, m0, where a equals 0 and b equals 0, results in f equaling 0. m1, where a equals 0 and b equals 1, produces f equals 1. m2, where a equals 1 and b equals 0, yields f equals 1. m3, where a equals 1 and b equals 1, results in f equaling 1. This truth table will without a doubt be utilized to fill the Karnaugh map in the upcoming step. We will fill the K-map layout directly from the truth table, mapping truth table to K-map cells. First, look at the input combination AB equals 0, 0. From the truth table, when AB is 0, 0, the output F equals 0. So we place a 0 in the K-map cell corresponding to row A equals 0 and column B equals 0. This is also called box 0 or minterm N0. Next, when AB equals 0, 1, the output F equals 1. We place a 1 in the K-map cell at row A equals 0 and column B equals 1. This corresponds to box 1 or minterm M1. Now, when AB equals 1, 0, the output F equals 1. So we place a 1 in the cell at row A equals 1 and column B equals 0. This is box 2 or minterm M2. Finally, when AB equals 1, 1, the output F equals 1. So we place a 1 in the cell at row A equals 1 and column B equals 1. This is box 3 or minterm M3. Understanding the filled K-map. At this point, the entire K-map is filled correctly. Each cell represents one input combination, matches one minterm, contains the output value taken directly from the truth table. Now we move to step 2. This is the most important part of K-map simplification, grouping adjacent cells and eliminating variables. Understanding the goal of grouping. The goal here is simple. Group adjacent ones. Identify the variable that remains constant. Discard the variable that appears in both its normal and complemented form. Group 1. Yellow group. Let us look at group 1, marked in yellow. In this group, variable B is common. Variable A changes. It appears as both A and A prime. So we eliminate A and keep B. Group 1. Proof check. Let us verify this algebraically. F1 equals A prime plus AB, factor B. F1 equals B A prime plus A. Since A prime plus A equals 1, F1 equals B, so this group simplifies to B. Group 2, green group. Now take a moment to focus on group 2, which is highlighted in green. In this particular group, variable A remains constant, while variable B undergoes a change. It shows up as both B and B prime. Therefore, we'll eliminate B and retain A. Group 2, proof check. Let us verify again. F2 equals AB prime plus AB. Factor A. F2 equals AB prime plus B. Since B prime plus B equals 1, F2 equals A, so this group simplifies to A. Final result. Now, we combine the results from both groups. Group 1 gives B. Group 2 gives A. So the final simplified expression is F equals A plus B. Now let us work through a 3-variable example using Karnaugh Maps, step by step. Problem statement. We are given the Boolean function f of a, b, c equals the summation of minterms 0, 1, 4, 5, and 7. This notation tells us exactly where the output f is equal to 1. Step 1. Prepare the truth table. The first step in any K-map problem is to prepare the truth table. Since we have 3 variables, a, b, and c, there are 8 possible input combinations, from M0 to M7. Assigning output values. Now we fill the output column f using the given minterms. From 0, the function is listed, so f equals 1. From 1, the function is listed, so f equals 1. From 2 and M3, the function is not listed, so f equals 0. From 4, the function is listed, so f equals 1. From 5, the function is listed, so f equals 1. From 6, the function is not listed, so f equals 0. From 7, the function is listed, so f equals 1. Understanding the table. This truth table now clearly shows which input combinations make the output true and which combinations make the output false. This table is the bridge between the Boolean function and the Karnaugh map. Step 2. Filling the 3-variable Karnaugh map layout. Understanding the setup. We are working with 3 input variables, A, B, and C. Since there are 3 variables, the total number of possible input combinations is 2 power equals 8. Thus, the K-map will contain 8 cells arranged in a 2x4 grid. K-map structure. In this layout, rows represent variable A. Top row, A equals 0. Bottom row, A equals 1. Columns represent variables B and C arranged in gray code order. 0, 0, 0, 1, 1, 1, 1, 0. Gray code is used so that adjacent cells differ by only one variable. This is essential for grouping later. Filling the K-map using the function. The given function is FABC equals sigma M 1, 4, 5, 7. This means the output F equals 1, 4, 5, and 7. So we fill the K-map as follows. At M1, we place a 1. At M4, we place a 1. At M5, we place a 1. At M7, we place a 1. All remaining cells, where the minterms are not listed, are filled with 0. Understanding the filled K-map. Now, the K-map visually shows where the output is true and where the output is false. This completed K-map is the foundation for the next step, which is grouping adjacent ones to simplify the Boolean expression. Now, we move to step 3, which is grouping the ones in the 3-variable Karnaugh map. The goal of grouping is to eliminate changing variables and keep only the common variables in each group. Group 1, yellow group. Let us start with Group 1, highlighted in yellow. In this group, variable A remains constant. Variable C remains constant. Variable B changes between 0 and 1. Since B changes, we eliminate B and keep A and C. So the simplified term for Group 1 is F1 equals AC prime. Group 1, proof check. Let us verify algebraically. F1 equals ABC plus ABC. Factor AC. F1 equals AC B prime plus B. Since B prime plus B equals 1, F1 equals AC. Group 2, green group. Next, look at Group 2, highlighted in green. In this group, variable A is constant. Variable B is constant at B prime. C changes, so we eliminate C and keep A and B prime. The simplified term becomes F2 equals AB prime. Group 2, proof check. F2 equals AB prime C plus AB prime C. Factor AB prime. F2 equals AB prime C prime plus C. Since C prime plus C equals 1 equals AB prime C. Group 3, red group. Now consider Group 3 marked in red. In this group, variable B remains B prime, variable C remains C. Variable A changes between A and A prime. So we eliminate A and keep B prime and C. The simplified term for this group is F3 equals B prime C. Group 3, proof check. F3 equals AB prime C. Factor B prime C. F3 equals B prime C. Since A prime plus A equals 1, F3 equals B prime C. Final result. Now, we combine the results from all 3 groups. Group 1 equals AC, Group 2 equals AB prime, Group 3 equals B prime C. So the final simplified Boolean expression is F equals AC plus AB prime plus B prime C. Now, let us indeed move on to 4-variable Karnaugh maps, which are quite commonly utilized in real digital design problems. Understanding the inputs. In this example, we have 4 input variables, A, B, C, and D. Since there are 4 variables, the total number of possible input combinations is 2 to the power of 4 equals 16. Therefore, the Karnaugh map will contain 16 cells. K-map size. A 4-variable K-map is arranged as a 4x4 grid. Each cell in this grid represents one minterm, ranging from M0 all the way to M15. Variable assignment. Now, let us understand how variables are assigned in the K-map. Rows represent variables A and B. Columns represent variables C and D. Both the rows and the columns follow gray code order, not binary order. This gray code arrangement ensures that adjacent cells differ by only one variable, which is essential for correct grouping. Understanding the layout, look at the K-map table presented. The row labels you see follow gray code 00, 01, 11, 10. Similarly, the column labels also adhere to gray code 00, 01, 11, 10. Each cell, let me emphasize, is labeled with its corresponding minterm number, which is beautifully shown in red. For example, the top left cell corresponds to M0, the bottom right cell corresponds to M10. The center cells include N12, M13, M15, and M14. Why is this layout important? This specific layout allows proper adjacency, wraparound grouping, formation of large groups, and guaranteed minimum Boolean expressions. Without gray code ordering, grouping would be incorrect. A lot of graphing. We are given the Boolean function f of a, b, c, d equals the summation of minterms 0, 1, 5, 7, 8, 10, 13, and 15. This notation means the output f is equal to 1 only for these specific minterms. Step 1. Prepare the truth table. Since we have 4 variables, a, b, c, and d, the total number of possible input combinations is 2 to the 4th equals 16. So the minterms range from M0 to M15. Assigning output values. Now, we fill the output column F based on the given minterms. For M0, M1, M5, N7, M8, M10, M13, and M15, the function is listed. Therefore, f equals 1. For all remaining minterms, the function is not listed. Thus, f equals 0. Understanding the truth table. Each row in this table represents one unique combination of inputs, A, B, C, and D, and the corresponding output value f. This table clearly identifies where the output is true and where the output is false. Why, oh why, is this step absolutely crucial? This truth table serves as the very foundation for the yes, indeed, Karnaugh map. If, by any chance, the truth table is incorrect, the K-map will, without a doubt, be wrong. The grouping will absolutely be erroneous. And, finally, the simplified expression will be, quite simply, incorrect. Now, let us move to step 2, which is filling the 4-variable Karnaugh map layout based on the given problem. The Boolean function is f(a)(b)(c)(d) equals sigma 0, 1, 5, 7, 8, 13, 15. This tells us exactly which minterms produce an output of 1. Understanding the K-map layout. This is a 4x4 K-map. Rows represent variables A and B. Columns represent variables C and D. Both rows and columns follow gray code order 00, 01, 11, 11, 10. Gray code is essential because it ensures that adjacent cells differ by only one variable. This allows valid grouping later, filling the K-map cells. Now, we place values into the K-map using the given minterms. At M0 and M1, we place 1. At M5 and M7, we place 1. At M8 and M10, we place 1. At M13 and M15, we place 1. All remaining cells where the minterms are not listed are filled with 0. Understanding the filled K-map. At this point, every 1 in the K-map corresponds to a listed minterm. Every 0 corresponds to a minterm not included in the function. Now, step 3, grouping for this 4-variable Karnaugh map. The rows are labeled using AB in gray code order 00, 01, 11, and 00. The The columns are labeled using CD in gray code order, 00, 01, 11, and 00. Based on the ones in the K-map, we form three groups, yellow, green, and red. Group 1, yellow, first. Consider Group 1, highlighted in yellow. This group contains two adjacent cells in the top row, where AB equals 00, under columns CD equals 00 and 01. Here, variable A is complemented, variable B is complemented, variable D is complemented, variable C changes, so it is eliminated. From the proof check, F1 equals A prime B prime C prime plus A prime B prime C prime. Factor the common terms. F1 equals A B prime C prime. Since D prime D equals 1, the expression simplifies to F1 equals A prime B prime. Group 2, green. Next, look at Group 2 highlighted in green. Observe the green group, which consists of two corner cells. Even though they appear far apart visually, remember that K-maps wrap around, so these corner cells are adjacent. In this group, A is unchanged, B is complemented, D is complemented, C changes. This again simplifies to F2 equals AB prime D prime. From the proof check, F2 equals ABC prime D prime plus ABCD prime. Factor the common terms. F2 equals ABD prime C prime. Since C prime plus C equals 1, this simplifies to F2 equals ABD prime. Group 3. Now consider Group 3, highlighted in red. This is a four-cell grouping in the center of the K-map. Here, B is common across rows 2 and 3. D is common across columns 2 and 3. Variables A and C change, so they are eliminated. Therefore, the simplified term is F3 equals BD prime, final result. Now we combine all group expressions. F equals F1 plus F2 plus F3. F equals AB prime C prime plus ABD prime plus BD. This is the final minimized Boolean expression, exactly as shown on the slide. Key observation. This example demonstrates valid 2-cell and 4-cell grouping, use of wraparound adjacency, how proof checks confirm correct simplification. That completes step 3, grouping, for this 4-variable Karnaugh map example. A max term. It is a Boolean term, you see, that evaluates to 0 for precisely one input combination. Max terms. Yes, they are utilized in the product of sums, or POS form. In Karnaugh maps, max terms correspond to zeros, not ones. 4-variable max term example. Now, consider this. 4-variable max term example. The Boolean function is given directly in max term form as f of a, b, c, d equals pi m of 0, 1, 2, 3, 4, 6, 8, 9, 10, 11, 13, and 15. This notation signifies that, hold on, the function output equals 0 for all of these specified input combinations. Conversely, the function output equals 1 exclusively for the remaining combinations. In the K-map, we shall place zeros at these max term locations. Then, we will group the zeros to derive the simplified POS expression. This marks the conclusion of our introduction to max terms and sets the stage for K-map grouping in POS form. Step 1. Preparing the truth table for our 4-variable K-map example. The Boolean function is given in max term form as f of a, b, c, d equals pi m of 0, 1, 2, 3, 4, 6, 8, 9, 10, 11, 13, and 15. Grasping the max term notation. Since the function is articulated in max term form, it signifies the function output is 0 for each of the enumerated max term indices. Conversely, the function output is 1 for all the other input combinations. Now, for the truth table construction, on the left side we enumerate all 16 conceivable combinations of the 4 input variables, A, B, C, and D, ranging from M0 to M15. Each row, if the index appears in the max term list, F is set to 0. If the index is not listed, F is set to 1. Observing the ones in the table, Based on this rule, the function output f equals 1 at n5, n7, m12, m15. All other rows have output f equals 0, exactly as shown in the table. Purpose of this step. This truth table is the foundation for the next step. Using this table, we will place zeros in the K-map because we are working with Maxterms. Then, we will perform grouping of zeros to obtain the simplified POS expression. Now, let us move to step 2, filling the K-map layout with Maxterms as 0. The Boolean function is given in Maxterm form as f of a, b, c, d equals pi m of 0, 1, 2, 3, 4, 6, 8, 9, 10, 11, 13, and 15, and in a 4-variable Karnaugh map. The rows depict A, B arranged in gray code order: 0, 0, 1, 1, 1, and 1, 0. Meanwhile, the columns illustrate CD, also in gray code order: 0, 0, 1, 1, 1, 1, and 1, 0. Each cell within the K-map corresponds to a unique Maxterm index, which is prominently displayed in red inside the cell. Because the function is expressed in Maxterm form, we follow this rule. Place 0 in the K-map for every index listed in pi m. Place 1 for the remaining indices. Accordingly, zeros are placed at Maxterm indices 0, 1, 2, 3, 4, 6, 8, 9, 10, 11, 13, and 15. Ones appear only at indices 5, 7, 12, and 14. Key observation. Notice that in POS simplification, we are indeed interested in grouping zeros, not ones. Now, we are at step 3, grouping. For this 4-variable Karnaugh map, because this function is given in Maxterm form, we focus on grouping the zeros. And since we are simplifying in POS form, each group produces a sum term. The final answer is the product of those sum terms. Group 1, yellow. First, look at Group 1, highlighted in yellow. This is a large grouping of zeros across the map. From this group, variable b remains constant. Variables a, c, and d change, so a, c, d are eliminated. So, the simplified term from Group 1 is f1 equals b. Group 2, green. Next, consider Group 2, highlighted in green. From this green grouping, a is complemented, d is complemented. Variables b and c changed, so b, c are eliminated. The constants map to the sum term. f2 equals a plus d plus. Group 3, red. Now look at Group 3, highlighted in red. From this red grouping, the constants a, d prime map to the sum term. f3 equals a plus d. Final POS result. Since this is POS simplification, we multiply the group terms. Phi equals f1 times f2. Substituting the results. Phi equals b times a times d. Key takeaway. Maxterms group zeros. Each zero group gives one sum term. Final result is the product of sum terms. Now let us understand Boolean factoring. Boolean factoring is the process of rewriting a Boolean expression by taking out common variables or terms, similar to algebraic factoring in mathematics. Basic factoring rule. Consider this expression, AB plus AC. Here A is common in both terms, so we factor it out as A times B plus C. This reduces two AND gates into one AND gate and one OR gate. We had noticed multiple examples in previous K-map problems. A canonical form is a standard way of writing a Boolean expression such that each term includes all variables. Every Boolean function can be represented in one or both canonical forms. There are two canonical forms. The first is canonical SOP, also known as Minterm form. In canonical SOP, the expression is written as a sum of products. Each product term contains all variables. The function is represented using sigma m notation. For example, f of a, b, c equals sigma m of 1, 3, 5, and 7. This means the function output is 1 for these minterms. The second form is canonical POS, also known as Maxterm form. In canonical POS, the expression is written as a product of sums. Each sum term contains all variables. The function is represented using pi m notation. For example, f of ABC equals pi m of 0, 2, 4, and 6. This means the function output is 0 for these maxterms. Canonical SOP expressions are simplified by grouping ones in the K-map. Canonical POS expressions are simplified by grouping zeros in the K-map. Canonical forms are therefore the starting point for K-map simplification. So remember, canonical SOP uses minterms. Canonical POS uses maxterms. Both forms are complete and systematic. Simplification comes later using K-maps or Boolean algebra. Now, let us understand how to convert between SOP and POS forms. Conversion is required because some Boolean functions are easier to simplify or implement in one form than the other. SOP to POS conversion. Assume the function is given in canonical SOP form as f equals sigma m of 1, 3, 5, and 7. Step 1. List all possible minterms. Step 2. Identify the missing minterms. The missing minterms are 0, 2, 4, and 6. These missing minterms become the maxterms, so the equivalent POS form is f equals pi m of 0, 2, 4, and 6. Canonical SOP and POS forms represent the same logic function, just written differently. Simplification using K-maps or Boolean algebra is done after conversion, not during conversion.